I'm Hyeoncheol from Korean University, and I will present on the topic on quantum cryptography with a focus on multi-party quantum computation. This talk is based on the paper titled Secure Multi-Party Quantum Computation with a Dishonest Majority. Here's the outline of today's presentation. So let's begin with the introduction. I'll explain the motivation behind multi-party computation, the challenges it faces, and the building blocks of our protocol. First, let's quickly revisit classical multi-party computation, or MPC. In MPC, multiple parties, each with their own private inputs, want to compute a joint function over all their inputs without revealing them to each other. Traditionally, this involves protocols that ensure privacy even in the presence of malicious parties. As you can see on the left, naive communication can lead to leaks and mistrust. However, with proper protocols, as shown on the right, parties compute functions securely, even if some are dishonest. However, when we move to quantum data, new challenges arise. Our goal is how can multiple distrusting parties jointly compute on private quantum data. Classical MPC works well for classical data, but quantum computing introduces entanglement and no-cloning restrictions. And furthermore, what happens if most participants are malicious? Can we still achieve secure computation? The core question we tackle is, can we build MPQC protocols that remain secure even if up to K-1 players are malicious? The answer from the paper is yes. The authors present an MPQC protocol that works for any number of players, tolerating an arbitrary dishonest majority. This is a major step forward compared to classical protocols, which usually require at least half of the players to be honest. Before we get into the protocol, we need to understand quantum circuits. A universal quantum circuit consists of Clifford gates, which are easy to simulate classically, and the T-gate, which is a non-Clifford gate and requires a special state called a magic state. Measurements which collapse quantum states to classical outcomes, and this diagram here shows how a T-gate is implemented using a magic state and auxiliary measurements. The next key building block is quantum authentication codes. To prevent tampering with quantum data, we encode states using a secret Clifford operation. Formally, we take an input state psi and apply a Clifford operation C, along with adding trapped qubits initialized to 0. To decode, we apply the inverse Clifford C dagger and measure the trapped qubits to check for integrity. This provides security against quantum tampering. Now, let's look at the threat model. We assume up to K-1 malicious players. Basically, everyone except one player could be dishonest. Adversary can deviate or arbitrarily from the protocol. Abortion of the protocol are allowed. Dishonest parties might abort midway, but even if they do, privacy and correctness of the computation are preserved. On the right, we see a formal security definition comparing the real-world protocol with an ideal functionality using a simulator. Finally, let's summarize the building blocks before we step into the protocol itself. Classical MPC protocols tolerant of abort. Quantum authentication codes to protect the integrity of quantum data. Magic state distillation for implementing non-Clifford gates, especially the T-gate. These three elements form the foundation of the MPQC protocol. Now we'll go step by step through the protocol itself and see how all these components come together. Let's start with an overview of the protocol workflow. First, we encode the inputs using quantum authentication codes. Then we prepare ancillary states as needed, followed by gate executions. If our circuit involves non-Clifford gates like T, we prepare magic states in advance. Finally, we perform decoding and output the results. Throughout, we continuously check for malicious activity. An important conceptual separation is protocol is between data flow and control flow. Data flow refers to the actual movement of qubits between players. Control flow is classical, an MPC protocol running in parallel, which securely manages encryption keys and verification steps. This separation ensures robustness against malicious interference. And now we discuss the design principles of the protocol. First, we use the trap qubits and public authentication tests to detect tampering. Second, the classical MPC controls the keys and verification process, keeping quantum data secure. Third, our protocol's security is proven using simulator-based arguments, providing strong theoretical guarantees. So this is the step one, input encoding. Each player encodes their input using random Clifford operations. Trapped qubits are inserted to detect any malicious actions. Importantly, the classical MPC securely stores the encryption keys, and initially, we might think to stack encodings, but this leads to very large ciphertexts. To manage this, we cleverly apply function like fc1, c2 to keep the ciphertext size manageable while preserving security. And this function f is calculated by classical multi-party computation. To ensure the correctness of the input encoding, we use the public authentication test. Here, player one prepares the initial state, applying random Clifford operation unknown to all players. The classical MPC selects a random linear transformation G and random Clifford C, and instructs player one accordingly, and player one applies operations and measures the traps. If the results match expectations, the encoding is authenticated successfully. So this is the summarization of the public authentication tests. One player performs the test by applying Cliffords and measuring the traps. All players verify the results through classical MPC, and these tests are versatile. They are used to both to test and initial encodings and to check whether computation steps are executed honestly. So once inputs are securely encoded, we move on to computation. The goal is to transform an authenticated state C into a new authenticated state C prime, where G is the gate we want to apply. We cover protocols for 1-qubit Cliffords, 2-qubit C0 gates, the non-Clifford T gate, and computational basis measurements. So let's start with the single qubit Clifford gates. Here, the trick is simple. We don't need to touch the quantum data. Instead, we update the classical encryption. The encryption key, if the current key is C, we updated it to C prime. After this update, decoding will yield to correct result G times psi. And secondly, CNOT gates are trickier. If we naively apply the same strategy, we run into trouble because the result is not in a clean product form. So instead, player one applies a carefully constructed operation involving fresh random Clifford C prime, and C prime one and C prime two. After this operation, player one performs a public authentication test to ensure correctness. This step prevents entanglement of the keys and maintains security. And next, we look at how we handle non-Clifford gates. The diagram here illustrates the process for applying the T-gate. Starting with the input state psi, we prepare an auxiliary plus vector plus state and apply the T-gate. Classical MPC collects the measurement outcome C, and depending on the value, applies fractions conditionally Pauli X gate and conditional phase gate. As a result, we obtain the desired output T times psi. Finally, the state is re-encoded, ensuring secure non-Clifford computation. And for non-Clifford operation, we need magic states. The process consists of two main steps. First, the cut and choose phase, where each player tests n random states using classical MPC. The remaining states are pretty good. And second, the magic state distillation step uses Clifford circuits to further improve the quality, leaving us with one very good magic state. Throughout this process, classical MPC coordinates the operations and ensures security. So now let's move on to the measurement step. In this phase, the player applies the operator V as instructed by the classical MPC V, consists of conditional Pauli X and Z operations along with the multiple SNAP gates. The player measures the state in the computational basis, obtaining an outcome R prime. Then the classical MPC checks whether R prime matches the expected value to ensure correctness of the measurement. This provides verification of the final result. The final step is decoding. Players receive decryption keys from the classical MPC, and they measure the trap qubits to verify the integrity of the state. Finally, they output either a classical result or a quantum state, depending on the application. So now let's move on to the security proof sketch. Our protocol achieves simulation-based security. In this model, a simulator emulates any malicious behavior in the idle world, ensuring no information leaks to adversaries. I will not explain specifically, but on the right, you can see how each part of the protocol is backed by a specific lemma of the theorem on the paper, such as lemma for input encoding and theorem for overall security guarantee. In conclusion, the real-world protocol is indistinguishable from the ideal world protocol up to negligible probability. And to elaborate the security model, first, composability. Secure subprotocols combine security to ensure end-to-end security of the entire protocol. And second, abort handling. The protocol allows aborting at any time without compromising privacy. Importantly, aborting the protocol does not leak any private information. To summarize the main results, our protocol enables secure multi-party quantum computation for any number of players. It tolerates up to k-1 corrupt players, and the encoded states are the size of 2n+1, which is much more efficient compared to the naive approach. For T-gate, we require only k and magic states. The round complexity for quantum communication scales at as order k times d plus log n, where d is the depth of the quantum circuit for C0 and T gates. And finally, there are some open problems and future directions. Developing a post-quantum secure classical MPC protocol for dishonest majority remains an essential challenge, and we should aim to reduce the round complexity for CNOT gates. Lastly, we should explore practical use cases for MPQC to better understand how this protocol can be applied in real-world scenarios. So this concludes my presentation, and thank you for every attention. And if you have any questions, feel free to proceed. Thank you.